Hi everybody, welcome back to the pre-recorded lecture, and today I guess I'm gonna explain one of the main theorems of the cluster algebra theory, and next lecture I'm gonna discuss this in more detail. So let me remind you what we did with cluster algebras, because it's been a while, we've been doing root systems, but now it's all gonna come together. So a reminder on cluster algebras. First of all, there was quiver mutation. As all of you are now experts in quiver mutation, so I don't even have to remind you what it is. In case you forgot, the definition is on the left. You start with a quiver and then you mutate at mutable vertices and they get new and new quivers. Similarly, there is seed mutation. So remember, a seed is a quiver Q together. Okay, so it's a pair of a quiver consisting of a quiver and a labeling of the vertices of the quiver by some rational functions. And when you mutate, you get some kind of mutated seed. Like this, and here q prime is just the mu sub k of q, and x tilde prime is, so x tilde is some labeling of my ice quiver by rational functions, and then x tilde prime is the same thing, except, so all of the entries stay the same except for the kth entry, which is, as usual, the product over incoming arrows plus the product over outgoing arrows divided by x sub k. And then we were talking about these cluster algebras of finite type. So again, the definitions are on the left. I guess one, yeah, let me mention them on the right as well. So by brackets q, I'm going to denote the mutation class of q, right, so the set of all possible quivers which are mutation equivalent to q, obtained from q by mutations. And also there's going to be q mut, which is the mutable part of q. And finally, finally there was two different definitions. One of them was for finite mutation type, in which would we say that in cluster algebras of finite mutation type is the, when you take the mutable part and then mutate only that mutable part in all possible ways, you get something that's, okay, you get a finite set of quivers. All right. Yeah. Okay. And so the second notion, which is going to be much more important for this in the next lecture, was of cluster algebras of finite type. So community is finite here, but here we get the stronger condition is that we get finitely many seeds. So the whole purpose of me introducing root systems and stuff like that was to be able to classify root systems, to classify finite type cluster algebras. And yeah, so problem that we're gonna discuss today is how to find all cluster algebras of finite type, which, by the way, right, so yeah, so the notion of a cluster algebra being finite type is that it's not obvious, but it's true that it only depends, so the property of being finite type only depends on the mutable part of your quiver, not on the seed, not on the frozens, but only on the mutable, on the way the mutable vertices are connected by arrows. And so an example that we studied in detail was that if q mut is in the path quiver, then triangulations tell us that the corresponding cluster algebra is finite type. I guess I have to be careful about the frozens in here, but anyways. There is some statement of the form that some cluster algebra corresponding to the path quiver is of finite type. But today we're gonna find all of them. And this is not the only one. There is a few more. Okay. So cluster algebras of finite type. Okay, now let me introduce a specific class of Dynkin diagrams. You can see I am kind of, so far, like up to this point, it's still not exactly clear, not at all clear what is going to be the relation. I mean, you can start, okay, let's say you can, in cluster algebras, you can start with some quiver, maybe something like this. And then you can assign some variables, and then you mutate in all possible ways, and you ask whether there's finitely many things you get, finitely many seeds you get. If you start with the Coxeter groups, so for cluster algebras you label it by like x1, x2, x3, x4, and then you mutate. For Coxeter groups, you can take the Coxeter graph as we discussed previously. Right, so you have these simple transpositions, s1, s2, s3, s4, and then you have relations like s1, s2 squared, so s1 and s2 commute. Yeah, let me write it down. s1, s2 equals s2, s1, etc. Plus there is relations like s1, s4, s1 equals to s4, s1, s4. And so here you are allowed to, so you start with, let's say, the Coxeter graph, or alternatively the kind of matrix Mij, and then you can take all possible products of these, like s1, s4, s1, s4, s1 times s3, s2, etc. And then you use the relations to identify some of these products. And so you can ask the question, like, is there going to be finitely many elements in the Coxeter group or not? And last lecture I explained that for this particular graph there is going to be finitely many, because this is the Coxeter group of type D4. And finally there is kind of related objects, these root systems, which here you don't even, I mean, you can eventually arrive at Dynkin diagrams, but originally you start with some vectors in some space, and then you ask for some symmetry conditions. So the relation between these objects is completely not clear, even though I explained the relationship between these two objects before. But to go from cluster algebras to any of these two things is not obvious. Okay, enough with that. Let me try to explain the result. So first, I'm going to restrict to a particular class of Dynkin diagrams. So definition: a Dynkin diagram gamma is called, well, there is usually two different words people use for this. So it's called either simply laced, or equivalently we're going to use ADE. So an ADE Dynkin diagram is a Dynkin diagram that does not contain multiple edges. If gamma has no multiple edges. Let me remind you what was the list of Dynkin diagrams. You can see that you have multiple edges for type B, C, F, and G. And you don't have multiple edges for types A, D, and E. And that's why, okay, A, D, E. These are the ADE Dynkin diagrams. And so it just happens that in this class we're gonna pay much more attention to ADE Dynkin diagrams than to other Dynkin diagrams. But in general, usually all the statements kind of generalize to, if you have some statement that's true for ADE, then it's true for arbitrary Dynkin diagrams. And we're gonna see this happen for cluster algebras today and next Wednesday. All right. So far I have defined an ADE Dynkin diagram. Now, all right. So what is the well, first observation is that these are all trees. Well, all these Dynkin diagrams are trees, but ADE Dynkin, they're just simple graphs, diagrams are all trees. And if you solved all the problems in the homework, one of them told you that if you have a tree, then any two orientations of a tree are mutation equivalent. Any two orientations of a tree. Right, so you take a tree and then you orient the edges so you get a quiver, and then any two such quivers are going to be mutation equivalent if the underlying tree is the same. The three are mutation equivalent. So this was proved in the homework that was due this Wednesday. Well, it depends on which week you're watching in, but the past Wednesday. Yeah, I guess I am ready to state the theorem. So now hopefully you see why have I been talking about root systems for no reason. Theorem. The theorem is that cluster algebras of finite type correspond to ADE Dynkin diagrams. More precisely, a cluster algebra for a given seed x tilde comma q is of finite type if and only if and only if what? If and only if the mutation class, so if and only if the quiver q mut is mutation equivalent to an orientation of an ADE Dynkin diagram. So yeah, I guess that's one part. So finite type gives you Dynkin diagrams, but moreover, different Dynkin diagrams give you different mutation classes of cluster algebras. Yeah, different cluster algebras. So moreover, different ADE Dynkin diagrams give rise, well, are not mutation equivalent. Let me just say this. Are not mutation equivalent. So in order to get all possible cluster algebras, you just start with a Dinkin diagram oriented in an arbitrary way, and then you mutate as many times as you want. You're going to get finitely many quivers, and these are going to be all possible quivers that give rise to finite type cluster algebras. That's it. And this theorem is due to Fomin and Zelensky. This was the second, like in the first paper in the series, they defined cluster algebras and proved the Laurent phenomenon. And in the second paper here, which is, I guess, yeah, the journal is not Annals anymore, but it's still pretty good. And so they gave this finite type classification. And so for the case of quivers, the answer is ADE, orientations of ADE Dinkin diagrams. And so now you have an interesting, you have a family of interesting questions, right? So for every ADE root system, you get cluster variables. Some of them are grouped into clusters. You get these quivers. Like you can study this combinatorics from a root theoretic point of view. And so, for example, I can ask, okay, question. How many cluster variables are there for a given ADE Dinkin diagram? There is going to be a finite number. What is this number in terms of the corresponding root system, let's say? Like what is the E6 number? And the answer is pretty beautiful. So let me show you an example. Well, let's start with type. Let's say type A1. And then the cluster variables are, so your quiver looks like this. It's just a single vertex labeled by x1, and then you mutate at 1, and then you get like 1 plus x1 over, well, sorry, you get just 2 over x1. And that's it. And then you mutate again, you get back here, so you get two cluster variables. Two cluster variables. And in type A2, you have this quiver labeled x1 and x2, and then you mutate in, like you mutate 1, 2, 1, 2, 1, 2, and you get, so what do you get? x2 plus 1 over x1. I'm just going to write down the seeds because the quiver doesn't really change. The quiver just, the arrow gets reversed every time I mutate. x1 plus 1 over x1, and then I mutate x2. I get, the first one doesn't change, but x2, instead of x2, I'm going to get x2 plus x1 plus 1 over x1, x2. And then I mutate at the first vertex again. I'm going to get, I think I'm going to get x1 plus 1 over x2. Right, there is going to be the Laurent phenomenon cancellation. And then finally, they're going to swap x1 plus 1 over x2. Is it going to be x1? Yeah, and then x2, x1. I think that's the mutation sequence for type A2. And so the cluster variables are x1, x2, x1 plus 1 over x2, x2 plus 1 over x1, and finally x1 plus x2 plus 1 over x1, x2. So the answer is that there's 5 cluster variables. And actually, we remember these mutable cluster variables, they correspond to diagonals in triangulations. So for type A1, you basically have a square with a diagonal like this, and then you mutate, and then you get a square with a diagonal like this. So these are the two cluster variables. These two diagonals correspond to cluster variables of type A1. And similarly, if I draw a pentagon, then the non-frozen variables are going to correspond to these 5 possible diagonals. So these are the 5 cluster variables. They correspond to diagonals which are not the sides of my pentagon. And similarly in type A3, because so far you see these like 2 and then 5, so you think Catalan numbers, but number of diagonals is not Catalan. Number of diagonals for the hexagon is going to be 1, 2, 3, 4, 5, 6, 7, 8, and there should be one more. 9. Yeah. So there in type A3 there's going to be A3 there is going to be 9 cluster variables. So they just correspond to the diagonals of an n plus 3 gon. But then that's type A. What about other types? What happens in type E, in type D5, let's say? And let me now make a nice definition. Right? If you remember these 5 cluster variables, they're going to be in bijection with some nice set of roots. And so the set of roots these are called almost positive roots. Definition. So you fix phi, just some crystallographic root system, then the set of almost positive roots is denoted by phi greater than or equal to -1. Right, it's like almost totally positive, but almost. And so it's just the union of the positive roots union with negative delta, where delta is a simple system. For example, so you take all positive roots together with these negative simple roots. For example, if you consider type A2, then the root system, the roots, they look like this. And so if this is your alpha 1, alpha 2, this is alpha 1 plus alpha 2. So phi plus is alpha 1, alpha 2, alpha 1 plus alpha 2. But then you include the negative alpha 1 and negative alpha 2. So these 5 guys are going to be, so let me just erase the last one. These 5 guys are going to be your, this is phi greater than or equal to -1. So you see there's 5 things. I mean, it's not hard to see that in general in type A, these the number of almost positive roots is going to be, like, the number of positive roots is n-2, and then you get n extra, well, n minus 1 negative roots, negative simple roots, and that's your almost positive roots. But in particular, if you compare these alphas to these cluster algebras, then they kind of look like they should be in a nice bijection with each other. Specifically, if you, so let me first explain the bijection in this case. So I'm gonna have a bijection which sends negative alpha 1, negative alpha 2, alpha 1, alpha 2, and alpha 1 plus alpha 2 to, the bijection is going to be x, this is going to correspond to x1, this is going to correspond to x2, alpha 1 corresponds to x2 plus 1 over x1, alpha 2 corresponds to x1 plus 1 over x2, and finally alpha 1 plus alpha 2 corresponds to x1 plus x2 plus 1 over x1, x2. So how am I doing this magical bijection? And the answer is that I just look at the denominators. I skip, I don't care about the numerators anymore, and so here the denominator is x1, x2 because I have alpha 1 plus alpha 2. If instead I have negative alpha 1, then the denominator is going to be x1 inverse. So yeah, I don't know if that really makes any sense, but let me state the precise theorem. So the theorem is that suppose that you have so gamma is an ADE Dynkin diagram, and let's say phi the corresponding root system, the crystallographic root system of type gamma, and then A the corresponding cluster algebra of finite type. So these are corresponding to gamma. Then I want to say that there is a bijection, then there is a bijection which is going to send, so I'm going to denote this bijection by alpha to x brackets alpha. And what it's going to do is, so it's a bijection between the set of almost positive roots and the set of cluster variables of my cluster algebra A. And it's going to work for arbitrary ADE and later for just arbitrary Dynkin diagram. And so what is I have to define x brackets alpha. And I'm not going to say exactly what it is, but I'm just going to say that x brackets alpha is the only cluster variable that can be written as so x to the alpha, some polynomial in x1, x2, all the way up to xn, right? So n is, I'm using r here, but n is usually the number of mutable variables. So I'm gonna fix n to be that letter. And so the condition on p is that where p belongs to, it's a polynomial with positive integer coefficients in the initial cluster, and so the denominator is just x to the alpha is x1 to the, so let's say alpha is written as c1 alpha 1 plus c2 alpha 2 plus etc. plus cn alpha n. Remember, the simple roots form a basis, so alpha can be written uniquely in this way, and these guys are actually, I guess I forgot to mention that whenever you write for a crystallographic root system, any root is any positive root is a positive integer combination of the simple roots. In general, these could be positive real numbers, but for crystallographic ones, these are actually integers. And these are precisely the integers that appear in the denominators of my cluster variables. So x to the alpha is x1 to the c1 times x2 to the c2, etc. times xn to the cn. I guess I'm saying that it's easier to define this bijection in the opposite direction. Whenever you find a cluster variable, you just look at the denominator, and then that's going to be a root in your root system, an almost positive root. Just like in this bijection here, I look at this guy, it has denominator x1, x2. Wait, have I? Okay, sorry, I have to add one more thing. So p is not just a polynomial, it's a polynomial. It's a polynomial with non-zero constant term. Any Laurent polynomial can be written uniquely as a ratio of a polynomial with a non-zero constant term divided by a monomial. And so that's what I'm doing. I'm looking at this. So here the constant term is 1, and therefore the denominator is x1, x2, so that corresponds to alpha 1 plus alpha 2. Here the denominator is x2, so you get alpha 2. And finally for x1, the denominator, right, so p has to have non-zero constant term. So p, in this case, p is equal to 1. Right, so x1 is equal to 1 over x1 inverse, where p has non-zero constant term, and then the denominator is a Laurent monomial. So it's allowed to have negative degrees. And the only way that's going to happen is when you, just for your initial cluster, you're gonna have these. Right? This bijection tells you that you only get positive roots or negative simple roots. And of course, the negative simple roots correspond to your initial cluster variables. So that's always going to be the case, right? So we always have at x, remember you have the notation x bracket alpha, so x bracket negative simple root is just going to be the corresponding initial cluster variable. Okay. Yeah, so this is nice. And then you can ask, it's pretty easy to compute for any, like these root systems, E6, E7, E8, D, N, they are given by just explicit set of roots. So you can count the positive roots very easily. While on the other hand, starting with a Dynkin diagram and then mutating in all possible directions is actually computationally very hard. And you get these huge, like these p polynomials, they are actually pretty big. You can read in the cluster algebras book. There's, for E8, the numerator is just crazy big. Yeah, and so yet somehow, if you only look at the denominators, then they're all going to be different, and then the number of cluster variables is just going to be easily computed from the root theoretic perspective, which I think it's pretty beautiful. Now you can ask other questions. You can ask, let's say, how many clusters, not just cluster variables. Cluster variables are grouped into clusters, like diagonals are grouped into triangulations. And so there's Catalan many triangulations. You can ask how many clusters for arbitrary Dynkin diagrams. You get some analog of Catalan numbers for arbitrary Dynkin diagrams. And I'm gonna discuss this a little bit later. So we'll discuss later, because now I wanna actually focus on on this kind of, there is this question which is that this is beautiful but not completely beautiful. The theory would have been completely beautiful if the answer was exactly all Dynkin diagrams, not just ADE. I mean, ADE is also pretty good. ADE Dynkin diagrams appear in a lot of contexts where other Dynkin diagrams don't appear usually. So, but still, it would be nice to kind of have cluster algebras correspond to all possible Dynkin diagrams, which is the same as like all semi-simple Lie algebras. And that there is actually the way the cluster algebras were originally defined was allowing you to prove this classification like on the nose, get all Dynkin diagrams. And so let me now proceed to the actual definition of cluster algebras. So far I've been only talking about quivers, but if you, I mean, and you, for the rest of the class, quivers are going to be enough. But for now, because maybe some of you later want to read some other papers on cluster algebras, many of them start with working not with quivers but with matrices. So I want to explain how to generalize the notion of a cluster algebra to a matrix instead of the quiver. So let me first motivate it by, so let me start with an ice quiver. Let Q be an ice quiver. So you have vertices. So the first n vertices are mutable, 1, 2, up to n. These are mutable. And then the rest, n plus 1, up to m. These vertices are frozen. And then there are some arrows between these vertices. And to this quiver, I'm going to associate a matrix. Right, that's going to be denoted B tilde of Q. So it's this is an M by N matrix, so it's going to be B tilde is going to be a skew symmetric matrix. Well, yeah, I guess I have to say it's going to have a part that's going to be skew symmetric. Okay, never mind. Let me first erase this. The way it's defined is just Bij is equal to, so it's equal to L if Q has L arrows from I to J. And also it's equal to L if Q to negative L if Q has L arrows from J to I. And finally it's 0 otherwise. So you just record the number of arrows between I and J and their direction. Because remember, you are not in a quiver, you are not allowed to have arrows from I to J and from J to I. So for every I and J, you're either going to have arrows like this, or arrows like this, or none of those. Let me try to draw an example. Let's say Q, I don't know, 1, 2, 3. Let's say 3 is frozen, and then you have 2 arrows here, an arrow from 1 to 3, 1, 2, 3, let's say 5 arrows from 3 to 2. Then the corresponding B tilde of Q matrix is going to be, so it's going to have rows labeled by, see in the definition it has M rows and N columns. So the rows correspond to all vertices and the columns correspond to the mutable vertices. The rows are labeled by 1, 2, 3 and the columns are labeled by just 1 and 2 because 3 is frozen. And the actual entries are, okay, so from 1 to 2 I have 2 arrows. So b12 is equal to 2. And b21 is equal to -2. Because I have -2 arrows from 2 to 1. And that's what I meant by saying that b is, it has a kind of a skew symmetric part. Finally, there is from 3 to 1 there is -1 arrow from 3 to 1, and there's also 5 arrows from 3 to 2. And that's it. So somehow I have encoded the whole quiver as just an m by n matrix. And I'm going to denote by b of q. That's the, it's called the principal part, or so it's principal, or also called mutable part of b tilde of q. This is just the submatrix, the top n by n submatrix of b tilde of q. So matrices are just a convenient way of encoding a quiver if you have a computer, let's say. And so in particular this principal part, b of q, is skew symmetric, which just means that bij is equal to bj is equal to negative bji for I and j in between 1 and n. So for mutable I and j, let me write it down more carefully, is equal to negative bji. Alright, now this is all nice, but then I have to explain to you, let's say I take my quiver and I mutate. In cluster algebras we mutate our quiver. So what happens to the matrix b tilde when I mutate my quiver q? Question. What is b tilde of, let's say I take a mutable vertex k of q, and then I mutate, and what happens to the matrix? And the lemma is, I think I have a lemma here. No, the point is that you can write it down purely in terms of the matrix, and it's even easier from the matrix point of view than from the quiver point of view. Because remember, for your quiver, you have to, okay, what was the mutation of our quiver, right? There is like step 1 is for each pair, like I goes to k goes to j, you create an edge from I to j. So if you have 5 arrows from I to k and 7 arrows from k to j, then you're going to have to create 35 arrows from I to j. And that somehow, like, it's easy to see that corresponds to just multiplying 2 entries of your B matrix. So let me just write down the B tilde matrix of a mutated quiver. So if I denote these new entries by B prime ij, then they're given by B prime ij. There's many ways to write down the matrix mutation, but here's I guess, yeah, that's the one that's easy to remember. So if you look at the 3 steps, the second step is you reverse all the arrows incident to k, and the third one is you remove all pairs of opposite arrows. So you just look at pairs of opposite arrows and you cancel them out, and that corresponds to subtracting bij from some, yeah, anyways, whatever. here is the claim that that's going to happen when you mutate. So first of all, the entries in, if you have your B matrix, and then you have some column labeled K, and then you have some row labeled K, then this row and this column are just going to be negated. Right? That's step 2. You just reverse. The arrows of K are just reversed. So Bij if I or j are equal to K. The interesting stuff happens when you mutate. So you have your vertex K, and then what's interesting is how the number of arrows from I to j changes as you mutate your vertex K. And it's going to depend on the number of arrows between I and K and the number of arrows between K and j and their directions. And the answer is given Bij plus Bik times Bkj if Bik and Bkj are both positive. So in other words, if you have, so what does it mean that Bik and Bkj are positive? That means that you have some arrows from I to K and some number of arrows from K to J, and then you just multiply the number of incoming arrows by the number of outgoing arrows, and you add that number to the number of arrows between I and J. So for example, if there was, let's say I had one arrow from J to I, and one arrow here and 2 arrows here, then I'm gonna add 2 arrows in the opposite direction from this arrow, and then so that's gonna cancel out, and that corresponds to precisely adding up these 2 things. Now I could also have arrows in the opposite direction. Bij minus Bik Bkj if Bik, comma Bkj are both negative. If I have arrows going like this, then I'm going to add arrows from j to I. And finally, in all other cases, like for example when I have arrows from I to K and from j to K, I don't create any new shortcuts. So I just get Bij otherwise. So just to recap, this step is step 2, which is we reverse the arrows. This is step, so that's step 2. This is step 1 plus 3. So you create shortcuts and you cancel pairs of opposite arrows. And finally, yeah, this is just what remains unaffected by steps 1, 2, 3. Okay. So far I started with a quiver, and then I created a matrix, and then I explained what happens if I mutate a matrix. Am I out of time? Yeah, let me just do one example. So let's say well, the point is that you can this operation is defined on arbitrary matrices. But and it turns out that the definition of cluster algebras works not just for skew symmetric matrices, but actually for skew symmetrizable matrices. And let me try to give you an example. I'm going to discuss this more next time, but let's say B tilde is given by I don't know, 0, yeah, -1, 2, 0, I don't know, 4, 1 or something like this. Yeah, let me even say, let me swap the signs for, let's say this is -1, this is 2, something like this. And then I perform mutation at row 1, row and column 1. So the rows are, let me label the rows B tilde, let's say the rows are 1, 2, 1, 2, 3. And then mu1 means that I negate all entries in the corresponding, the first row and the first column. 1, 2, 1, 2, 3. So 0, 1, -4, -2. And then this is going to be 0 because there's always no arrows from a vertex to itself. And finally, what happens here is interesting, right? So if I want to compute bij for I equals to 3 and j equals to 2. And so I look at, and k is equal to 1. So I look at the entries bik and bkj, which is 3, 1 and 1, 2. And I notice that they are of the same sign. They are both positive, so that corresponds to this case here. And since they're both positive, then I add their product to bij. So instead of 1, I get 1 plus 4 times b32 is b prime 32 is b32 plus b31 times b12, which is 1 plus 4 times 2, which is 9. So a computer can do this operation much better than a human, and you can very easily program this and observe that for some matrices things blow up, and for some other matrices things stay kind of bounded. And yeah, so next time I'm going to explain that the finite type cluster algebras associated to matrices actually correspond precisely to Cartan matrices, or in other words, Dynkin diagrams of not necessarily ADE but arbitrary. So that's it. Thank you, and I see you all on Wednesday.